In this video, Ian reaches for the chair and he's performing shoulder flexion and elbow extension. When he pulls the chair towards his body, he's performing shoulder extension and elbow flexion. Later in the video, I'll focus on elbow extension and flexion to help explain the agonist, the type of force, arthrokinematics, active force, passive force, and my two free body diagrams. Ian's moving in the sagittal plane and is using a medial-lateral axis. We know this is the sagittal plane because his movements are dividing the body into left and right sections. We know that it's a medial-lateral axis of rotation because he's performing flexion. Ian is performing an open chain action because his distal segment of his kinematic chain is not fixed to the earth or another immovable object. His hand is moving towards his torso, and so pretty much this means that his distal end is free to move, and it's a little, his elbow joint is a little bit less stable than it might be in a closed chain. The agonist muscle group is the group that is most directly related to the initiation and execution of a particular movement. So when Ian extends his elbow to reach for the chair, his agonist muscle is his bicep, and that's being elongated in eccentric activation. When he pulls the chair towards his body, he's performing concentric activation of his bicep. So for the arthrokinematics, we're looking at the humeral ulnar joint, which is the elbow joint. So this humeral ulnar joint is a hinge joint, and because it's performing an open chain, it is concave, acting on a convex surface. So this means that the ulna is rolling and sliding in the same direction. When Ian's elbow extends, his olecranon fossa rolls and slides inferiorly. When he flexes his elbow, his olecranon fossa rolls and slides superiorly. Active forces with Ian throughout his entire task. Both concentric and eccentric movements create sarcomere cross bridges. So it's the eccentric activation of the bicep that we see a greater active force with Ian's motions. During elbow extension, Ian is producing active and passive force. Passive force is a force that is initiated in a muscle after Ian's muscle hits a critical length, and as the muscle continues to lengthen, the force will build and provide different levels of resistance throughout the motion. Force modulation is directly proportional to, but not equal to, torque modulation. Torque takes into account both lever arms and forces a muscle produces. For example, longer lever arms for a muscle attachment will contribute to more torque, but not more force. With Ian, we're looking at his biceps brachii, and we see that we're working with a third-class lever, and therefore a shorter lever arm for the muscle attachment. Ian will require more force for torque production because his lever arm is shorter. To modify this, we can produce a larger torque while requiring a smaller force of the muscle. To produce more torque, Ian could stand closer to the chair so that his angle of insertion is not only closer to 90, producing more force, but he also uses more time to lengthen his bicep, so a slower contraction would produce more torque here. Here I've put Ian in elbow extension, and I've drawn two segments, and also the joint, which is shown by the blue circle. Right, next I'm adding in an arrow to represent muscle force. So it attaches right about here, and then it's pulling up here. Okay. The next force I'm adding in is gravity. So it'll be the blue arrow, about 2/3 of the way down the shaft. Here's the fulcrum. Oh, shoot. Next, I'll divide the two forces that I've put in by adding x and y coordinates. My and mx. Mx always being the one that runs along the shaft, and y perpendicular, running away from the shaft. Okay, 90 degrees there. Lastly, I'm adding in joint reaction force, which always runs opposite to the muscle pull.
quick note, muscle pulls causing rotation and compression.
And this concludes Ian's eccentric free body diagram. For our concentric free body diagram, I again have started putting in both the shafts, so that's in green, and then representing the joint is the blue circle. And again, I'll add in muscle pull here, so that's in red, and then force of gravity, which goes straight down towards the ground. I'll divide both of these forces by adding in the x and y coordinate system. It's kind of at 90 degrees, but not quite, so I'll add it in for the muscle pull here. Alright, and then for gravity. Oops. Kind of goes like that. Have our y's and our x's. And here's joint reaction force, going the opposite direction of the muscle. We know that concentric activation is both rotational and distractive. And this concludes our free body diagram of concentric activation.